Artificial intelligence, machine learning, and deep learning are often used interchangeably, but they are not the same. This video provides a structured comparison to clarify how these concepts relate, where they differ, and why using precise definitions matters for design, evaluation, and decision-making. The most helpful way to understand these terms is hierarchically. Artificial intelligence is the broadest category. Machine learning is a subset of AI, and deep learning is a further subset of machine learning. Artificial intelligence refers to systems designed to achieve goals using computational processes. These goals may involve reasoning, planning, perception, or decision-making, depending on the system. AI is not a single technique. It includes many approaches developed over decades, ranging from symbolic logic and search algorithms to learning-based methods. Some AI systems do not learn at all. They rely on predefined rules or logical structures and behave deterministically according to their design. Examples include expert systems and planning algorithms. These systems follow explicit instructions rather than adapting from data. Machine learning is a subset of AI focused on systems that improve performance by learning from data rather than relying solely on predefined rules. The core idea of machine learning is pattern discovery. Models analyze data to identify relationships that support prediction or classification. Unlike traditional programming, machine learning systems are shaped by data. Behavior emerges from training rather than explicit instruction. Common machine learning tasks include classification, regression, clustering, and anomaly detection, each addressing different problem types. Machine learning models include decision trees, linear regression, support vector machines, and ensemble methods. Machine learning often depends on feature engineering. Humans select and design inputs that represent relevant aspects of the problem. Machine learning is flexible and efficient for many problems. It balances performance and interpretability when data is structured and well understood. However, machine learning struggles when features are difficult to define or when data complexity increases significantly. Deep learning is a subset of machine learning based on multi-layer neural networks. It addresses limitations of feature engineering. The defining feature of deep learning is automatic representation learning. Models learn features directly from raw data. Deep learning requires large data sets. Performance improves with scale, making data availability essential. Deep models are computationally intensive. Hardware acceleration, particularly GPUs, is critical for training. Examples of deep learning models include convolutional neural networks and transformer architectures. Deep learning excels with unstructured data such as images, audio, and text, achieving high accuracy. Its limitations include high cost, difficulty in interpretation, and sensitivity to data quality. Visually, AI covers the broadest scope, machine learning occupies a smaller subset, and deep learning is the most specialized. Data requirements increase from AI to ML to DL. Deep learning typically demands the most data. Compute requirements follow a similar pattern, with deep learning being the most resource-intensive. Compute requirements follow a similar pattern, with deep learning being the most resource-intensive. Flexibility also changes. AI emphasizes goal logic, ML emphasizes statistical patterns, and DL emphasizes representation learning. In email filtering, simple AI rules may block known patterns, while ML classifiers learn from labeled examples. In image recognition, classical ML struggles with feature design, while deep learning learns visual representations automatically. In language translation, deep learning is essential due to scale, complexity, and contextual dependencies. Choosing the right approach depends on the problem, constraints, and available resources, not on trends. Rule-based AI works best in stable, regulated domains with explicit logic. Machine learning is often sufficient for structured data and moderate complexity. Deep learning is appropriate when data is unstructured and complexity is high. Accuracy gains must be weighed against cost, latency, and maintainability. Deployment constraints influence model choice. Hardware and response time matter. Maintenance differs across approaches. Rules require updates. Models require retraining. Error behavior varies. Rule-based systems fail predictably. Deep learning can fail unexpectedly. Risk profiles differ. Transparency and control decrease as complexity increases. Governance becomes more important as opacity increases. Oversight mechanisms must adapt. Terminology misuse fuels confusion. Marketing often labels all systems as AI regardless of method. Precision improves design decisions, evaluation, and communication. Avoiding category errors prevents unrealistic expectations and misapplied solutions. Many real systems combine rules, machine learning, and deep learning pragmatically. Industry practice favors hybrid approaches over theoretical purity. Clear conceptual separation supports effective learning and skill development. Public understanding improves when hype is replaced with accurate distinctions. Artificial intelligence focuses on goals, machine learning on data, and deep learning on representations. Comparing scope, data needs, and compute clarifies appropriate use cases. The key takeaway is that these approaches complement rather than compete with each other. Next, we will examine the main types of learning used in AI systems, starting with supervised learning.